All right, welcome back to another lecture here talking about carbonium cations. I want to encourage you to keep practicing arrow pushing mechanisms. We've started to put additional challenging problems on those problem sets, ones that we have no intention of grading at the end, and they're challenging. Work with other people, ask anybody you know, if you're working in a lab, ask other people, work with others, come to our study halls and get some extra guidance. But you have to keep practicing these problem sets. In addition, we've given you problem sets out of the Introductory Organic Chemistry textbook that we use here at UC Irvine by Janice Gorzinski-Smith. Work the arrow pushing problems in that book. You know, in theory, they're designed to be targeted at the level of a sophomore organic chemistry class here in the United States, but it turns out they're actually quite challenging, and you'll get a lot out of practicing reactions that you supposedly had during your second year, but actually will turn out to be quite challenging when you start drawing the arrow pushing mechanisms. So practice drawing arrow pushing mechanisms using the rules that we've given you in this class and the tools that we've given you in this class. We've been talking about carbonium cations, things that stabilize them. Kind of obviously lone pairs can donate into a carbonium ion and stabilize it, right? Carbonium ions hate having only 6 electrons. But in this lecture, and we've talked about pi bonds donating, resonance, allocations, benzyl cations. But in this lecture, we're talking about sigma bonds and their ability to stabilize carbonium ions. And sometimes that's easily connectable to things like bond length, like these long carbon-silicon bonds. We'll see a lot more of that after we've talked about how to draw substitution mechanisms at silicon. We spent some time talking about these strained bonds and all that P character, super nucleophilic. Look for cyclopropyl carbonyl cations. These are special types of carbonium ions. They're not always going to be obvious in the mechanism. I'm not going to do anything extra to make them obvious to you, but you'll have to be looking for those when you start drawing the arrow pushing steps. And today we're going to focus on kind of the same concept, but different concept, and that is the overlap, orbital overlap. If you have well-aligned bonds that can align with empty p orbitals, they can provide stabilization. And that stabilization of the carbonium ion isn't just there in the products, in the carbocation products. All of that donation was there in the starting materials, helping to push out the leaving groups. So this isn't just an effect where, oh, if I just predict the more stable products, I'll always know it's faster. Don't get caught in that trap. All these effects were there in the starting materials, making it easier to push out leaving groups. I want to come back over and take a look at these bicyclic ring systems. These are special ring systems called Norbornyl ring systems. That bicyclic, the nomenclature would be a bicyclo 221 ring system, but we call that a Norbornyl ring system. And you've probably seen these before, generated through Diels-Alder reactions when you took an introductory organic chemistry course. Let me give you 2 completely inexplicable observations. So first observation is you can take this isomer that I've drawn here. If you might recall from the nomenclature that we gave you when you learned about Diels-Alder reactions, this is referred to as the endo isomer. This will be more obvious why that's called the endo isomer. And this one down below here is called the exo isomer. They're diastereomers of each other. And if you take the endo isomer with a tosylate leaving group or some other sulfamesylate leaving group, doesn't matter, and you treat it with potassium acetate, you'll substitute that leaving group. That seems kind of obvious. There's nothing controversial or inexplicable about that. So let's go ahead and draw out what product you would expect if you did a substitution reaction, just using basic principles of inversion of configuration at the stereocenter. So I would kind of expect that acetate group, I'll just write it out as OAC, that's an ester, should have the opposite configuration at that center. That's kind of obvious, so that's not inexplicable. But here's what's inexplicable, right? What's inexplicable is that this is racemic. The product, the starting material was one enantiomer, but the product is racemic. And that means that there was an equal amount of the product where you substituted it over here on the other side. Now, how are you going to explain that? Right? Nothing you have been taught in sophomore organic chemistry is going to help you understand what's going on there. Let me go ahead and draw out that enantiomer, just so we're clear what I mean by an enantiomer. Both stereogenic centers are now inverted. And so now this other enantiomer that you generate is the mirror image. So you generate both of those enantiomers here. What's going on? Something weird is going on. And I can tell you from mechanistic studies that this is not an SN2 reaction. It's not a simple SN2. Okay, so, what happens if we take the exoisomer? What happens if we start with the leaving group sticking up? If the leaving group is initially pointing upward, what are we going to get as the product? Well, you get the same things. You get the same product. In other words, you substitute with retention of configuration. This group here, the acetate group, the nucleophile, is still in this exo orientation just like the leaving group was. And it's still racemic. It's like, gee, what's going on here? Something's going on. We're going to need to explain this. This ring system is special, and it merits some discussion because when you look at natural products that are isolated out of plants, you find this Norbornyl ring system very commonly. It's an easy ring system to generate using Diels-Alder reactions, super common in organic synthesis and organic structures. Let's go ahead and go deeper into what is it that makes this Norbornyl ring system special. Okay, so we're going to have to do some practice drawing conformations. When I took sophomore organic chemistry and more advanced organic chemistry classes in undergrad, I used to just spend hours practicing drawing chairs. You probably do the same thing. I don't know. Sitting while you're eating lunch and you're drawing chairs. You're in the bathroom and when the mirror's fogged up, you're drawing chairs wherever you can. And it may sound obvious, but if you want to understand the Norbornyl ring system, a lot of the publications that are out there will tend to draw it like this because they want to emphasize the difference between exo and endo substituents. The exo substituents are on the top, and then the endo substituents are on the bottom. I'll just write exo and endo, and you might have learned about that when you talked about Diels-Alder reactions. When you draw it like this, it looks to me kind of like a coat hanger in some ways. Don't draw it like that. If you draw it like that, you're going to completely miss the point. So I'm going to show you how you should draw Norbornyl ring systems so that you're ready to draw complex organic structures and appreciate things like bond staggering and chair-like conformations. So we're going to draw our Norbornyl ring systems based on a chair. You need to learn how to draw a good chair. And the essential ingredients for drawing a good chair, I use this program called Chem that has 2 different chairs that it automatically draws every single time. I invariably pick the wrong chair just like you when I start drawing, and so it allows you to draw 2 different chairs. I'm showing one of these 2 chairs here actually. There's a different flipped chair version that looks a little bit different. If you wanted to draw a chair from scratch, the single most important thing for you to do is draw 2 bonds that look like this. If you can start like this, you've got the whole chair. And the thing that I did when I drew these is I was absolutely careful to make sure this carbon over here is not vertically aligned with this carbon. That way when I draw axial bonds, the bonds won't be on top of each other. So here's the way you start. If you know how to draw a chair, the way you start drawing a Norbornyl ring system is that you come over and you bisect the chair in one of 2 positions. So it depends on which kind of Norbornyl ring system I wanted. So if I wanted to draw a chair, I would come over here and I would draw a bond right here. I'm going to get rid of that end carbon on the right side. But before I do that, let me draw a bond to make a 5-membered ring. Norbornyl rings have 5-membered rings. That's what we want to focus on. And we want that 5-membered ring to be drawn well so we can pay attention to bond staggering. If I wanted to erase the carbon on the left-hand side, I would bisect it right here. And that leaves me with 2 amazing carbons, these 2 right here and these 2 right here, that are not vertically on top of each other. Right, there's some space. So let me go ahead and draw some axial bonds on those 2 carbon atoms. Let me just go ahead and redraw my bisected version here. And now I've got 2 leftover atoms where I can draw axial bonds, and they need to be perfectly vertical. And I'm going to make sure they're exactly the same length. If you're drawing bonds where one carbon-carbon bond is 4 times the length of the other, there's no way you can possibly appreciate conformation. So when I come over here and I draw this back bond, I'm going to put a little gap in there so I can tell it's in the back. I'm going to make sure that's the same length. That doesn't sound so hard. Just make sure those those axial carbon-carbon bonds are the same length. So over on this bottom chair where I bisected it, I'm going to draw axial bonds here, and I'm going to make sure those bonds are the same length. There we go. Boy, look, I've got a 5-membered ring, and I've got 2 axial bonds on each of those 5-membered rings. That's not that hard. So let me just keep going here. Remember, I was supposed to be bisecting these. Now I'll just redraw these axial bonds here, but now I'm going to join them. Now I can see my Norbornyl ring system in there. It's got this extra cyclopropane, but I can see that Norbornyl ring system. And I've drawn it two different ways based on where I chose to originally bisect. So there's my Norbornyl ring system. Do you see that Norbornyl ring system starting to appear here? It's this part right over here. It's this part right over here. And all I have to do is erase that extra cyclopropane, and I've got Norbornane. And I can perfectly pay attention to axial bonds. Let me go ahead and finish that up over here. So I had my Norbornyl ring system. I've got my Norbornyl ring system, and I've erased the extra carbon, but I've got these perfectly axial bonds, perfectly straight up and down, like that. Same length of carbon. If I make these axial bonds the same length, when I join them, I'll end up with a nice angle there. And using this type of drawing, I can still see the difference between an exo and an endo orientation substituent. So if you want to become a real expert at drawing to make things, notice how I darkened the bonds here. You know, things that are closer to you appear bigger. So the bonds that are closer to you, if you make them bold, it really, you know, screams out at you about the relative locations. Now, why would I want to pay so much attention to basing my drawing on a chair with vertical axial bonds, right? Why not draw it like this, where the axial bonds are not vertical? Well, if you learn how to draw chairs and you learn how to draw Norbornyl ring systems based on chairs, you will be prepared to explain why this atom over here is very good at attacking on the other side of that ring. And if you can't draw chair-like conformations, you'll never be able to grasp that. Drawing chair-like conformations helps you to pay attention to bond staggering and antiparaplanar relationships. That's critical for understanding things like the E2 reaction. Helps you to understand conformations and reactivity in bicyclic systems. So because I chose to draw this Norbornyl ring system down here as a chair, it's easy for me to fuse another chair onto there. Watch this. I'm going to fuse another chair so that I can pay attention to what does this other ring system look like. So the true structure of this has an axial methyl group sticking up. It has this Norbornyl ring system. And when I draw this hydroxyl group going down, it should be quite clear to me that there's no problem for that to reach over and displace that. And if you couldn't draw these ring systems based on chairs, you would never know that that oxygen is getting right in the face of that methyl bromide bond, of that carbon bromide bond. Right? It's right there. It can't get away. You'll have no problem cyclizing that and making a tetracyclic ring system. So this is why it's important to draw chairs, Norbornyl ring systems, based on chair conformations. Okay, so we don't do a lot of conformations in this class, conformational analysis, but we are talking about Norbornyl ring systems. Okay, let's come back to this exo-Norbornyl tosylate sulfonate with a sulfonate leaving group. This is the exo-isomer that I talked about. And if you have an exo-tosylate and you make that leave, if I pop off this tosylate and I leave behind a carbonium ion right here, there's going to be an empty p orbital. And I've kind of sketched that out for you. Here's that empty p orbital. But notice this bond down over here. There's a bond down over here on the bottom, that bold bond. And it is axially aligned just like the p orbital. It is right next door to the p orbital. It is the electrons in this yellow bond are overlapping in space with that empty p orbital. And if they are overlapping in space, they are donating into that p orbital. And when you donate into an empty orbital, you stabilize the system. You cannot stop this vertically downward carbon-carbon bond from stabilizing this Norbornyl cation. And that effect was there in the starting material. That effect of this bond was already donating into sigma star before you did anything. Before you drew the carbonium ion, that donation effect was there. So let me not draw that in the starting material. Now, this donation is so powerful. Boy, in the early days of organic, I say early days, in the 60s, people argued, screamed at each other at national meetings about what was the meaning behind this. And the arguments before we had electronic structure calculations, computer calculations, were these, is this donation so powerful that this bond is literally migrating over? And if it can migrate in that direction, that means it can migrate back. If you migrate that bond and do a 1-2 shift, now you're set up to shift backwards and forwards. 1-2 shift, backwards, forwards, 1-2 shift. 1-2 shifts are pretty good. But the question arose, is this just a very fast 1-2 shift, or are these just resonance structures of each other? Now, if you've got this carbon-carbon bond back here donating into the backside of this orbital, that means you can't attack with a nucleophile on the backside. There's already something donating there. If you want to come in with a nucleophile, you have to come in opposite that CC bond that's already donating. So it kind of restricts the trajectory for attack so that you have to attack from the top or the exo face of this Norbornyl ring system. There is no alternative here. If you make a carbonium ion like this, you have to attack that from the top face. So is this a resonance structure, or is that bond just migrating back and forth, doing 1-2 shifts back and forth? We now know that these are just resonance structures of each other. The true picture of this is somewhere in between. It's not like two isomers rapidly going back and forth. That's not reality. You can synthesize this carbocation and put it into solution because we now have superacids. And this carbon atom that's at the bottom of this carbon atom at the bottom, it's over here at the bottom, is directly between those two carbon atoms that it's migrating back and forth. Now, we don't have a good way to represent this, right? How do we represent this? Do we draw dashed bonds for that bond that's migrating back and forth? You know, it's hard to draw this with anything based on a chair, but this would be a truer picture of that Norbornyl cation. If you can make that Norbornyl cation, that would be the picture of that. And so we're kind of stuck here. This is the best picture we have for what that looks like. And in fact, if I drew it like this, the truth would be not this rapid 1-2 migration. The truth would be that I've got 3 centers. We call this a 3-center 2-electron bond. Is it a 1 bond or 2 bonds? Or 2 half bonds? What is that? I don't know. People call it a 3-center 2-electron bond, but the bond is actually spread across 3 atoms. The problem with this true representation is we can't use dashed bonds for arrow pushing. So this is why we're not going to draw this representation in our class. We can't use it for arrow pushing. I'll just say not for arrow pushing. You won't get any good results. You'll end up with the wrong charges if you try to use dashed bonds for arrow pushing. Now, it might bother you that the right structure can't be used for arrow pushing, but you've been confronted with that before. Do you remember when you used to do electrophilic aromatic substitution and you used bonds in the benzene ring to attack things? But that picture of bonds in benzene rings isn't accurate. If you look at a benzene ring, the pi system is distributed across all 6 atoms of that benzene ring. The bond order is not 2. The bond order is not 1 for those carbon-carbon bonds. The pi bond order is 1.5. Right? This is the truth here for a benzene ring is that each of the CC bonds in that benzene ring has a 1.5 bonds. The bond order is 1.5. That's the way a benzene ring looks. But in my class, do not draw benzene rings with dashes on the inside. Don't draw benzene rings with those stupid circles on the inside. I understand you're trying to convey the bond order is 1.5, but you can't push arrows with a circle. You can only push arrows with correct Lewis structures, and that means single bond or double bond. So, we have to make a choice here in this class, since we're interested in predicting chemical reactions, we're going to rely on arrow pushing, and we can't use dative bonds, dash bonds, or hydrogen bonds for arrow pushing. So this is one of those instances where I expect you, when you see a Norbornyl cation, to know that there's this powerful bond donation, this donation of a bond. I expect you to know that the Norbornyl system is distributed on these 2 top atoms here, and here, but we're only going to draw these either one or the other. Yeah? So the question is, can you draw circles in a if you have some benzene ring that's far away from the reactive center, can you draw a circle in there? No. Not in my class. Here's why. Look how quick this is. 1, 2, 3. Are you saying that's so much slower than drawing a circle? Yeah. Just draw the 3 bonds. Because sometimes you never know. There can be benzene rings far away that look like they're not involved or look like they're not ligating the palladium atom. And then you find out later that, yes, the pi bond was donating into something, and you'll have those bonds available. So I don't want to sound like a jerk. I just want to get you thinking about arrow pushing and Lewis structures. When you get outside of this class, you draw as many circles as you want. But since I make the rules in this class, don't draw the circles. So, okay, we can't easily depict the correct structure for a Norbornyl ring system. I expect you to know that this bond is powerfully donating into that empty p orbital. And I will allow you to draw this as though it's a 1-2 shift, a stepwise 1-2 shift. I will allow that in this class. So if you choose to draw this for any arrow pushing mechanism, I'll accept this. You know, I would also accept it if you drew, so this is okay if you draw equilibrium arrows, even though that's not true. So okay for this class. And this is a better thing to do, is simply to draw it with a resonance arrow. This is the preferred. I'll just write preferred here. Just draw a resonance arrow in there. And it shows that you know that these are just two different ways to depict one species. But if you draw the equilibrium arrow, I do that sometimes because it's easier to view it as a 1-2 shift. I'll accept that. Okay, so, but I expect you to see that that perfect bond is just sitting there, right next to the empty p orbitals, jamming that electron density into that, to the back, onto the bottom side of that empty p orbital. Now, this is not just a regular bond. Somebody went through and analyzed the amount of p character. You know, 5-membered ring is not a 6-membered ring. The 5-membered ring, the bonds are a little bit contracted, and it turns out that the bonds in this bond here, these bonds that you have, based on the bond angle, have extra p character. They're not 109.5. They're a little bit contracted, right? They're 103 degrees. So there's extra p character in that bond. Those bonds are a little bit more nucleophilic than a regular CC bond that's simply migrating and doing a 1-2 shift. Okay, Norbornyl cation is pretty amazing. You know, it's pretty amazing it can do all that stuff. I think we probably have some problems, challenge problems on your problem set that involve Norbornyl cations, and you're thinking, oh yeah, I get it. No, you don't get it. Once you start drawing the mechanisms and you've got 6 different shifts in there, you're suddenly going to have a middle, your 8th structure is going to be, oh yeah, that's a Norbornyl cation. I didn't see it coming. It's hard to see when that's coming. Did you have a question, somebody? Or, okay. Okay, so let's talk more about shifts. Right, shifts. Let's talk about shifts where there's a real shift and not just some sort of a resonance structure between things. Here's a not simple case, but it looks simple. But and I'm sure you've talked about this exact rearrangement in your sophomore organic chemistry classes. But if you take a secondary alkyl tosylate or you protonate the alcohol and make it into a leaving group, that's not easy to leave. Because you'll end up with this secondary carbocation, and nobody really wants a secondary carbocation. That's not going to just sit there. You might hope that a nucleophile will be able to work its way in there and attack that, but something's going to happen sooner than that usually. Right? You can't do a Friedel-Crafts reaction and attack that with a benzene ring because rearrangements happen too quickly. But there's 2 possibilities here. Let me show you the obvious possibility here. The obvious possibility is that we migrate that methyl group here. And that should be kind of obvious, I think. I don't know if that's obvious. And if I migrate that methyl group, I'll get a new carbonium ion that looks like this. The methyl is now over here, and now the positive charge is over here at the top. Now, that wasn't the only possibility. Do you see the other possibility? It's as plain as day. There's hydrogen atoms that we didn't draw on here. There are CH bonds that are right next door, just like the carbon-methyl bond. And we should already know that 1-2 migrations of H's are also fast. And so why is it that we don't see this? How come we don't have this kind of migration occurring here to make and do a hydride shift instead of a methyl shift? Isn't hydrogen lighter? I mean, what about hydrogen being lighter, and shouldn't that be just as good as the... Look at the problem here. The problem is that if you migrate the hydride into a hydride shift, you still have a secondary carbocation. There was no thermodynamic downhill driving force to do the 1-2 shift of the hydride. It's not like all things were equal. Do you want to migrate to give a more stable carbocation or one that sucks just as much? That's easy. That's an easy decision to make. 1-2 shifts are super fast, especially if they make more stable carbocations. And if they don't make more stable carbocations, then that's not so good. And the problem with this is you have to be able to see CHs that we don't draw for you. You need to be able to know every single CH that's in your molecule, even though they're not drawn. You have to see those. Now over here, I'm back in this same situation. I've got this tertiary carbenium ion, this tertiary carbocation that has these groups here. And is this going to be stable? That carbenium ion has H's next door, it has methyls next door. So is it possible for this group over, this methyl group, to migrate right back where it started from? Absolutely, that's possible. That's fast. Tertiary carbenium ions are stable, and it's fast for that, or kind of fast. Well, actually, let me say not. There's a faster thing. I'll say, let me take out the word fast, because there's something that's faster, and I want to put this into. I want to reserve the word fast for the fastest possibility here. So, the fast thing to occur, there would, if you were to measure it, would be for the lighter hydrogen to migrate. Right? The other possibility is for this hydrido group to migrate over there. I would expect that to be a little bit faster. And that would put this plus charge back. Now, you wouldn't know that this is occurring because by symmetry, these two molecules are identical if I move the hydrido group over there. But I would expect that hydride migration, this 1-2 shift, backwards and forwards to be fast. The methyl group could migrate. Oh wait, I don't know what I was saying here, but this backwards migration would give me a secondary carbocation. That would be slow. The forward direction is fast, but migrating back to give me a secondary carbocation, right, this is tertiary. Migrating back to give the secondary, that would suck. That's not going to happen quickly. So what you would expect to get at the end of this process would be this equilibrating mixture of these tertiary, then they're the same by symmetry. You'd get a tertiary carbocation, which could then do something. You pull off a proton to make an alkene, you attack it to make an alkyl chloride or an alcohol. This would be the expected mode of reactivity. Now 1-2 shifts, the bottom, are fast. I want to take a look at this. Here's a case where you got 3 different methyl groups next to a carbenium center, or carbenium cation center. Somebody went through the process of measuring the rate at which these methyl groups migrate back and forth. And it turns out that the free energy, the transition state free energy, is less than 5 kcals per mole. Jeez, that is low. Most reactions that you're in the lab running, they've got free energy, transition state energies that are like 25, 30. Maybe you're heating them if you're 30s. 5 kcals per mole. If you convert that to factors of 10, this is blazing. This thing is occurring, this rearrangement is occurring 1 billion times a second. The methyl groups are migrating. If you somehow labeled one of those carbon atoms with a C13, it would scramble in seconds. All the methyl groups would be scrambled due to this very fast migration in this system. Okay, so 1-2 shifts are favorable. They're super favorable if you're going from a less stable carbenium ion to a more stable carbenium ion. Be looking for that. Let's go ahead and take a look at a difficulty, though, because I'll often ask you to suggest a plausible arrow-pushing mechanism for this reaction. And most carbenium ion reactions occur under acidic conditions. Right? We're not trying to do E2 eliminations. We're trying to use acid to protonate a leaving group, or the conditions happen to be acidic because you're generating toluene sulfonic acid as the product. Most carbenium cations, or you're making them using a superacid. But here's the problem when you're running things under acidic conditions. When you run carbenium cation reactions under typical acidic conditions, typical means that there's some sort of a counterion there. I'll draw it as A-. That could be a sulfuric acid conjugate base called bisulfate, could be tosylate. There are things in there with lone pairs, and it is fast to do 1-2 shifts. But if you've got something with an oxygen lone pair in there, there's an alternative mechanism you can draw for this. And that alternative mechanism looks quite plausible. The alternative mechanism would be to pull this proton off to generate an alkene, and I promise you that's a good reaction, and then re-add the proton to the other carbon. You can't tell from my arrow pushing where that proton's going to end up, but I'll show you like that. Now, both of these are plausible mechanisms. Now, in this class, I never ask you draw the mechanism for this reaction. I ask you to draw a plausible arrow-pushing mechanism. And in this case, you don't know what is more plausible. Is it a 1-2 shift, or are you protonating and then deprotonating? You can't know that. You know, I would probably draw this as a 1-2 shift, but I couldn't rule out this protonation and deprotonation, or the deprotonation and reprotonation process. So they're both plausible, and I would accept either of those. If you were trying to move the if you were trying to move the proton, I would accept either one of these mechanistic possibilities for moving the proton from one carbon to the other. If there was some A minus that had, for example, oxygen, lone pairs, or a chloride. Okay, you know, this idea of overlap, that Norbornyl ring system has great overlap of a strained bond that has extra p character. 1-2 shifts, the neighboring bond is right there. It's kind of obvious that there's good overlap. If you're right next door to the carbocation, you're a bond with electron density. It's easy to understand that there would be good overlap. But there are cases in organic chemistry where you can see much longer range hydrido group migrations. Let me show you an example here. Here's an example it's kind of hard to believe, but somebody went through the trouble of showing what was going on here. So here's a transformation that is deceptively simple. So you're losing a tosylate group, and then you're making an alkene. It's kind of like some sort of an E1 elimination reaction or something like that. But, you know, what's just happened here, right? I know you can all see that we formed a CC double bond. Don't get focused on that. That's not at all interesting. The interesting thing is that there's now 2 H's over here on this carbon that had the tosylate. And if you're looking carefully, you can see that there used to be an H here that's no longer there. A hydrido group has leapt across the ring and landed on the opposite side. That's what happened here. Now, how do we explain that? And this is just all about overlap. Turns out that 8-membered rings and 9-membered rings suck. They suck. Because when you try to draw them out, I'll try to draw out an 8-membered ring in a more realistic conformation. This would be a more realistic conformation for an 8-membered ring. There's this massive bumping. You can't generate these. It doesn't look like a stop sign, right? If you try to get as close as you can to 109-degree bond angles, you end up with something where there's this bumping between the 2 carbons. If you try to synthesize 8-membered rings by cyclization, you're going to get burned. If you try to synthesize 9-membered rings by simple cyclization reactions, you're going to get burned because this bumping hurts you so much. And that bumping is there. That bumping, I'm going to try to draw this in some sort of a shape where, I don't know if I can do this here. Let me try to draw this in some sort of a shape where I can see what's going on. I don't know if you'll be able, this would be the shape of this. There's a methyl group here, and there is a hydrid, a CH bond on the bottom. And that tosylate group is getting ready to leave. Let me darken the bonds that are closer to us so it has this kind of fancy look to it. Here we go. You can't stop that bumping there. When I draw it like that, it's kind of obvious. Oh yeah, that CH bond and all its electron density is kind of getting into the business of that tosylate sigma star. Right? If you generate the carbonium ion, the H is ready to hop out. Or the other way to look at it is the electrons in this CH bond are already donating into the sigma star. I'll go ahead and draw it via a carbonium ion mechanism. So once you generate this carbonium ion, let me draw the carbons in front of us first. I'll darken those bonds because they're closer to us. Here we go. Then I'll draw the bonds in the back. So if you generate this carbonium ion, I'll draw the H here because there is already an H there. And now I draw this hydride that's in the middle. It's now easy to see why this happened. Right? that CH simply leapt across the ring and then generated this, there's two, you leap across the ring and then you deprotonate to finish up that E1 elimination mechanism. You generate a new carbocation. I'm not going to draw that carbocation in the middle. So now you'll generate a tertiary carbocation. It's that bicyclic thing. Okay, so good orbital overlap. You can get hydrides to migrate longer than just 1-2 shifts. I don't know, what is this? Like a 1, 2, 3, 4, like a 1-5 shift? It looks like it's leaping through space, but it's actually right there next door to the carbonium ion. You know, George Olah invented this, I don't know if he invented it, but he won the Nobel Prize for his work in superacid chemistry that allowed his group to synthesize and then study, take NMR spectra of carbonium ions by protonating off leaving groups and having no nucleophiles around that could attack them. And so if you make the Norbornyl cation, this may be kind of obvious, but if you make a Norbornyl cation, these H's that are on the top, the XO-CH's, can migrate over. There's fast 1,2 shifts that are occurring in a simple, unsubstituted Norbornyl cation. That 1,2 shift would be fast. And that 1,2 shift can go backwards and forwards. You can migrate right back there and shift the CH right back. 1,2 shifts, fast. Those are fast. But there's another shift that's occurring, and you wouldn't have known if you weren't Ola studying this. What he found is that these CH bonds that are on the bottom here, that one right there, can also shift. It's not as fast, but they can leap across 3 atoms and do a 1,3 shift. The Norbornyl ring system is special. Things are so crowded in there. You're not going to see 1,3 shifts in typical systems, but in the Norbornyl ring system, there is this surprising 1,3 shift. Don't invoke this in other systems that aren't Norbornyl. There is a surprising 1,3 shift that's not surprising if you can look at the 3-dimensional structure and see how close those are in space. So, okay, that's sigma bonds. It's kind of amazing. If you get good overlap, sigma bonds can donate into carbonium ions. They can migrate, they can stabilize them. It's happening, and you'll see a bunch of mechanisms involving these things on our problem set. All right, we're going to shift gears now in a big way. Boy, I'm tired of carbocations and carbonium ions. I hope you're tired of them too. Now, I don't hope you're tired of them because they allow us to really bring up concepts of bond nucleophilicity and donation into empty orbitals. And now let's go and start talking about, right, we've been talking about empty p orbitals. We're going to go in order here. So we've been talking in this class about addition to empty p orbitals. Let me create a little space here. We've been drawing addition to empty p orbitals by lone pairs, non-bonding lone pairs, by pi bonds, which are more not quite as nucleophilic as non-bonding lone pairs. And then we finished by talking about electrons in sigma bonds and their ability to donate into empty p orbitals. But now, instead of talking about empty p orbitals, let's move on, because it's not like everything's carbocation chemistry. Let's start talking about addition to pi star orbitals instead of carbonium ions. This is a big shift for us. We're getting off of carbonium ions. We're going to talk about things adding into pi star orbitals. So we need to talk about pi star. And this is one of the most common arrow pushing steps, second to proton transfers. This is the most common type of arrow pushing step for mechanisms in organic chemistry. Okay, let's start with a simple carbon-carbon double bond. Before we start talking about heteroatoms and stuff like that, can we add to CC double bonds with a nucleophile? Can we get a nucleophile to attack a CC double bond? And let me start off at the bottom here. Is this reasonable? Does it seem reasonable for us to take like an alkylithium, like butyllithium, and just attack a CC double bond? And I'm taking an alkylithium because I know that's powerfully nucleophilic. I would hope you would know that too. Turns out that that's not a good reaction. Now, it's surprising because it is very good to take alkylithiums and Grignard reagents and add them to carbonyls. That's fantastic. All kinds of nucleophiles can add to carbonyls. Right? I hope you would know that. Lots of nucleophiles. It could be alkoxides can add to carbonyls. Amines can add to carbonyls. Grignard reagents can add to carbonyls. That bond, that carbon-magnesium bond. Of course, alkylithiums can add to carbonyls. Enolates can add to carbonyls. Enamines can. We're going to see all kinds of nucleophiles adding to carbonyl groups. But what's wrong with this alkylithium thing? You can actually get some alkylithiums to add to some double bonds. You just want to make sure that you're trying to go downhill in energy instead of uphill in energy. So later we're going to talk about the relative stability of alkylithiums. Tertiary and secondary alkylithiums can add to alkenes under certain conditions as long as you make a more stable alkylithium. You can't go uphill in energy. And so in this case, you can go from a secondary alkylithium to a primary alkylithium. That's favorable, and you can do those reactions. Now, most people don't have a tank of ethylene gas to use as a starting material, but right? You could imagine a situation where you go from a tertiary alkylithium to a secondary, and those work. They're just not very common. They're not synthetically that useful for you. But addition to carbonyls is a common bond-forming process. That's the much more common version. And you would expect that addition to carbonyls would be faster, because if I draw out the energies of the molecular orbitals here, you would expect that a pi cc, a pi star cc that's this high in energy is higher in energy and harder to add to than a pi star CO. Replacing one of the C's with an O should make an orbital that's lower in energy and easier to add to. It's easier to add to carbonyls with nucleophiles than it is to add to simple alkenes. I don't think you ever saw anything like that in sophomore organic chemistry. All right, so we're going to see all kinds of stuff. But let's go a little bit further about the relative reactivity of carbonyl derivatives. There's all kinds of carbonyl groups that you can add to. Amides, esters, aldehydes, ketones, cyclic carbonyl compounds, lactones, and they're not all equally reactive. And so we need to start talking about how does the substituent that is next to a carbonyl affect the relative reactivity. I'm showing you down below some numbers, but in order to help us understand the numbers at the bottom of the page, let's go ahead and talk about two different effects of the neighboring substituent, especially if it's a heteroatom like nitrogen or oxygen or chlorine. And the problem here is that there are two opposing effects. One makes it easier to add to the carbonyl, the other effect makes it harder to add to the carbonyl. So which effect wins? Well, I'm going to have to tell you, because you couldn't possibly know, right? You couldn't draw some MO diagram that tells you, which thing gets lowered more, or the other type, when you've got two opposing effects, somebody has to tell you which one wins, and you do that by running an experiment. So the first effect that we'll describe here that affects the reactivity of carbonyls would be resonance. If I've got a lone pair right here on this neighboring atom, that lone pair can donate in to the carbonyl. It creates a new pi-like orbital that's spread across 3 atoms, and that new orbital is going to be harder to add to. It decreases the rate of nucleophilic attack. Decreases the rate at which the nucleophile can attack. Right? If you've already got the nitrogen lone pair adding in, how's that nucleophile going to add in? It's already crowded in there. Not sterically crowded, but there's already something in there donating. Now there's a completely different effect of the nitrogen atom. It has nothing to do with resonance. And it has to do with the fact that nitrogen has more protons in the nucleus. Nitrogen is more electronegative. So there's this polarization effect, a polarity effect. Some people call it an inductive effect or something, right? This nitrogen is going to be pulling, it creates some sort of a field that makes it more negative, and conversely, it makes this carbonyl carbon more partial positive. That makes it easier to attack. It increases the rate at which nucleophiles will attack. This secondary effect that's also occurring, both effects are occurring. It increases the rate at which nucleophiles attack. So the polar effect, that's an electronegativity effect, increases the rate at which nucleophiles. So which effect wins? Well, let's go down to this table I made here and look at the relative electrophilicity of carbonyl derivatives to understand which effect wins. What I'm going to do is I'm going to take over here a simple ketone that has 2 methyl groups. Maybe I should compare it with it. And then compare that with a system that has a nitrogen atom. If I put a nitrogen atom there, does that nitrogen atom of an amide make the carbonyl easier or harder to attack? And here's that simple amide derivative right here. This is the amide. The amide is less reactive. It's 10 million times less reactive. It's 10 million times harder to add to an amide carbonyl. So which effect wins? Yeah, resonance is more powerful here. Resonance wins. The resonance effect deactivates the carbonyl more than the polar effect activates it. Now, the effect is not quite so large with oxygen because oxygen is way more electronegative. So you can see, right, the ester is less reactive, but not by 10 to the 7. It's only 10 times less reactive, but that's still substantial. Now, are these numbers accurate to 0.1 decimal? No, they're not. I mean, maybe in some cases it'll be 100 times more reactive, but Esters are traditionally more reactive than ketones if all things are equal, right? The resonance effect wins. It's more important than the pull. Now let me come back over here to another heteroatom, chlorine. Well, that's more reactive. Didn't we say that resonance was always more important? Why is it that the acyl chloride is more reactive? It can't be that the resonance effect wins. What's going on with chloride? Yeah.
Maybe because it's like it's fine as like a anion, so like the prop is like stable as it's fine with the charge.
Well, we haven't formed an anion yet, and the effect is there in the starting material. Yeah.
Is it just because, like, overall the resonance contribution of a halide is going to be less, and once it reaches a certain point?
Yeah, why is it going to be less?
The energy below there.
Could it be the bond?
Yeah, the bond is long. The chlorine is just too darn far away from the carbonyl to have effective overlap. Right? You just don't get effective pi bonds to third row, fourth row atoms. The resonance is not so good. Yeah, it's this. You'd see the same thing with a sulfur atom. The sulfur would not have effective donation. All right, so this is the relative ordering. If you put if you put two nitrogens here, this is called a urea. When you put two nitrogens next door to a carbonyl, it's a functional group. You don't see that often. 10 billion times less reactive than a ketone, right? If you put two nitrogens on there. So this is the span of reactivity of typical carbonyl groups. And if you have no electrons, no bonds, no nothing like this, I don't want to draw lone pairs on the H. There's no lone pairs on H's. Boy, formaldehyde is just crazy reactive. This is why you can't buy formaldehyde. If you buy formaldehyde, it's a polymer. The lone pairs of one formaldehyde oxygen add to the carbonyl of another, and it just forms long polymers. You buy the polymer of formaldehyde called paraformaldehyde. It's not stable as the monomer because it's so reactive. Okay, we're going to stop right there. And what are we going to talk about? When we come back, we'll just talk about more examples that are based on these effects. You know, aldehydes are more reactive than ketones. Ketones are more reactive than esters and amides. And what are some of these substituent effects there? Keep practicing arrow pushing problems. Get your hands on one of these Smith textbooks and practice arrow pushing problems from the back. Practice working the extra challenge problems on our problem sets. Get together with your friends, come to our study halls that me and Jason have, and we'll help you.